Hello, this is Dr. Hassan with Innovate, and this is lecture number 66, Implementations of Synchronous Sequential Networks, of Chapter 9, Design of Synchronous Sequential Networks of the course Digital Logic Design or Digital Systems or Digital Electronics. And this is a disclaimer for you to read. I cite 3 references in Digital Logic Design, however, there are many books related to Digital Logic Design. In Chapter 9, we have 4 steps to design any synchronous sequential network. The first step, which is the most important step, is the derivation of state graphs. Then, once we have the state graph, we will reduce the state graph or reduce its state table to reduce the number of flip-flops needed to implement the network. Then we do state assignments to reduce the hardware necessary to build the network. Then we do implementations. Once we have the state assignments, we do implementations. And if we like to implement with programmable logic devices, we will use VHDL language. VHDL allow me to design the code necessary to implement the network. Then we can generate the netlist file and we download it to any PLD or FPGA. Guidelines. After the state graph and the state table have been derived from a given problem statement, and after the state table has been reduced to a minimal number of states, and after a suitable state assignment has been found, the following procedure can be used to realize a sequential network with flip-flops and combinational logic, which is simply logic gates. The procedure, step number 1, form the transition table, also known as an excitation and output table, by substituting the derived state assignment to each corresponding state in the reduced state table. The resulting transition table specifies the next states of the flip-flops and the outputs in terms of the present states of the flip-flops and the inputs. Step number 2, plot next state Karnaugh maps for each flip-flop and derive the flip-flop input equations. Also plot the present output maps and derive the output equation or equations. Note techniques developed in previous lectures are very useful in Chapter 7, are very useful to determine the input equations for D, JK, T, and RS flip-flops. Step number 3, realize the flip-flop input equations and the output equations using available logic gates for programmable devices such as PAL, PLA, or RAM. Step number 4, check your design by signal tracing, laboratory testing, or computer simulation. And this is really will be the end of the design, the complete design of synchronous sequential network. And this would be mainly the goal of this lecture and the goal of this chapter and mainly the goal of this course. Example. We'd like to reduce a given state table and find a suitable state assignment. Form the transition table and realize the network using D flip-flop, JK flip-flop, T flip-flop, and SR flip-flops and available gates. Now you should be aware, and you have the knowledge now, to reduce any state table by using any method. And the easiest method that we use is by inspection. So we can inspect this table, and if we look at the present state A has the next state D and B. The present state B has the next state A and B. And the state C has the next state A and C. And the state D has the next state NID. So there's possibility that A and B are equivalent because they have the same output, 1 and 1. And there is possibility also that C and D are equivalent because they have the same output, 0 and 0, the same output Z. Now, clearly, what we see here that state C and D, they have the same function, or they resemble each other, and they are equivalent. Why? Because if the present state C and x is 0, I go to state A, and I will remain in state C if x is 1. If the present state D and x is 0, I will go to A, and I will remain in state D if x is 1. So clearly both of them, they will remain in the same state. So they have the same function, or they resemble each other. So therefore they are equivalent to each other. So if C is equivalent to D, I can remove D and replace D in the table with C, so I get the following table. ABC, if the present state is A, the next state is CB, 1, and if the present state B, the next state is AB, and the output is 1, and present state C, the next state will be AC, and the output will be 0. Now you should remember how to use the guidelines for state assignments. And guideline number 1 will look at present state who has the next state, the same next state for a specific input. So for x is 0, for instance, I have A, the next state, and A for the state B, and A for the state C, for the present state C. So BC must have agency, must be adjacent to each other, or they must be located at the next cells in K-maps. The same thing if we look when x is 1, the present state A has the next state B, and the present state B has the next state B. So AB must have adjacent to each other, or must be adjacent to each other. Therefore, the first guideline will have BC and AB, BC and AB. BC because they have the next state A, and AB because they have the next state B and B. Now, guideline number 2, we are looking for the next states for each present state. So I have BC, AB, and AC. BC, so guideline number 2 will be BC, AB, and AC. And guideline number 3, present state that they have the same output, same present output, and I have AB. AB must be adjacent to each other. Okay, so AB. So clearly AB repeated in every guideline, guideline 1, guideline 2, guideline 3. So I must meet AB. So I place A at the M0, the midterm 0 cell, or all 0 cell. This is Y1 and Y2. We call the flip-flop Y1 and Y2 because it's a 3-state machine, so we need 2 flip-flops. So we placed A and we placed B here, so we meet AB. I have to meet BC, so I will place C here. So I have BC. So I met BC and AB from guideline 1, and I met BC and AB from guideline 2, and I met AB from guideline 3. Okay? I cannot meet AC because they are diagonals. So they are not adjacent to each other. So with this, I have the state assignment A 0, 0, the state assignment B is 0, 1, and the state assignment for C is 1, 1. C 1, 1. I will go and form the transition table. It's very easy. The transition table comes from the state table. I will replace A with the value of the state assignment. So A will be 0, 0. B will be 0, 1, and C will be 1, 1. So I did this, 0, 0, 0, 1, 1, 1. And Y1, Y2 for the next state, we have when X is 0, I have CAAA, CAA. So A 0, 0, and C is 1, 1, so it will become 1, 1, 0, 0, 0. And I have under X is 1, I have the state B, B, C. And what's B? B is 0, 1. Also, I'll put 0, 1, 0, 1, and C 1, 1. And Z, the output Z will stay the same, 1, 1, 0. So once I have this, I can have the K-map for Y1 and K-map for Y2. K-map for Y1 and K-map for Y2. So the K-map will be implementation of D flip-flop X, Y1, Y2, 0, 1. So I have 1, 0, 0, 1, 0. Don't care 0 because I have one state is missing, which is 1, 0. I never used it. Okay. So we do this. See here? This came from Y1, which is 1, 0. Then 1, 0 is not used, so it's don't care 0. And 1, this is for Y1, under X is 0, and under X is 1 will be 0, 0, don't care 1. So 0, 0, 0, 0, don't care 1. 0, 0, don't care 1. The same thing Y2, we have the K-map for Y2 and Y1. But we know from the characteristic equation for the D flip-flop that Y1 is equals to D1, or D1 is equals to Q1 plus, which is here is Y1. And Y2 will be equal to D2, and Z is 1, 1, 0, so it's very simple. So what we can find the switching equations for D1, which is Y1, D2, and Z. So we say D1 is Y1, which is X prime, Y2 prime. This is from K-map. Or X, Y1. And D2 will be X or Y2 prime. Or it is X prime, Y2 prime, all prime. So to implement with all NAND gates. And Z simply is Y1 prime. Okay, so Z will come out from Y1 prime. Okay, so we implement with the type flip-flop. Now, we can use the same K-maps to implement with JK flip-flop, T flip-flop, and SR flip-flops. So we did this in the previous lectures, as we said. Okay, for the JK flip-flop, I will go to the Y1 map, and based on the characteristic equation, I will divide the map to two maps. Okay, map to find J1, which is the upper side of the map, because the characteristic equation says Q plus equal to JQ prime, or K prime Q. So what I will go to the J1 map where when Y1 is equals to 0, so this map I have only 1, I simplify for the 1, and I get basically J1 equals to X prime, Y2 prime, X prime, Y2 prime, because we are in the Y1 equals to 0 map to find J1. I go to the y1 equals to 1 map, which is the lower portion of the map, and to find k1. So I will simplify for the zeros. What I will get x prime. So k1 will be x prime. The same thing, I will divide the map to y2 prime, or y2 equals to 0, which is the upper two cells and the lower two cells. And since I have 1, 1, don't care, so I can group them all as a one group to find J2, and J2 will be equals to 1 because everything canceled out horizontally and vertically, and J2 will be equals to 1. I will go to those 4 cells, the inner 4 cells, to find K2, and then we'll simplify for the zeros, so I will get x prime. So K2 will be x prime as you see it. Z did not change, it's the same came up, which is y1 prime. Again, we need only one AND gate, or we can use NAND gate if you want to. AND gate to limit J1. K1 is x1 prime, so I have x, and K2 is x1 prime, so this is x1 prime will go to K2. Okay, and x2 prime, the same thing. x1 prime, x prime, I do apologize. X prime will go to K2, and x prime will go to K1 because K1 and K2, they are the same. So we need to complement x. And J2 will be either open circuit, or we take it to +1 or +5 volt. Okay, or logic 1 switch will deliver J2 is equals to 1. And Z will be Y1 prime. C will be Y1 prime, so we will take it from Y1 prime. So by doing this, we implemented with JK flip-flop. Full implementation JK flip-flop. Now, with T flip-flop, we can develop actually T1 and T2 based on the characteristic equation of T1 and T2, because T1 will be equals to Y1 and capital Y1 exclusive or capital Y1. So it's small y1 exclusive or capital Y1. And this will allow me to get T1. The same thing with T2 will be the exclusive OR of Y2, small y2, and capital Y2, the exclusive OR between capital Y2. So we'll get those two maps. Or we can derive the map simply from the original map. See, if we take the original map, which is here, okay, when y1 is 0, okay, so those values T1 will become, because 1 plus 0 is 1, 0 plus 0 is 0, so they remain the same. While when y1 is 1, we will take the complement, so 0 will become 1, and don't care will remain don't care. So this is what we see here with the T1, the 1, 0, 1, don't care, 1, don't care. Okay, the same thing with the second column. So we can apply really without going to develop the table. We can derive T1 and T2 map from simply from the original next state maps, which is capital Y1 and capital Y2. So with this, we have the maps. Since we have the map, I will simplify and I find T1 and T2, and I implement them simply with NAND gates. Now, as we know, the SL flip-flop is slightly tricky, and we need to find S1 and R1 values and S2 and R2 values from the transition requirement table, which I will remind you with the transition from 0 to 0 we need S to be 0 and R to be don't care. Transition from 0 to 1, it means from Q to Q plus, or Y1 small letter small y1 to capital Y1. So 0 to 0, we need S0 and R don't care. 0 to 1, we need S1 and R0. 1 to 0, we need S0 and R1. And 1 to 1, we need S to be don't care and R to be 0. And again, we can derive it from Y1 map with the transition table in front of us, the transition requirement table. Okay, and we can derive those map S1 and S2 and R1 and R2, and we simplify the equation so we get S1 will be x prime y2 prime, R1 will be x prime y2, S2 will be y2 prime, and R2 will be x prime y2 and z y1 prime. And we can implement all this with 2 gates. That's it. Okay. So what we did, we implemented a complete network using D flip-flop, using T flip-flop, using JK flip-flop, and using SL flip-flop and gates. And this will conclude really the implementation lecture for chapter 9. I thank you very much for listening. Please subscribe. Hopefully to see you very soon in the next lecture. Sincerely, Dr. Hassan.